So our topics for today lecture is deep learning and general image classification. So we will concentrate both on traditional approaches and deep learning based approaches, but we will start from problem definition. So our topic is image classification. Let's find what is it. We have some digital image represented in form of pixels, and we need to categorize it according to main visual content or object. So this is sheep, this is person, this is cat, and this is car. What is its application? Why it is so important? We meet with this problem in different areas. For example, we have some image and we want to classify, is it a suitable image for us, or maybe it's some not suitable. For example, some spam, some problems with violence, with naked image. Maybe we have a picture from autonomous navigation system, for example, robot, and we want to try to understand where it's located, what it does it see. Maybe so in some system that retrieves some images, some image system that get images from camera, we want to know what happens. Also, it's very important in medical area, like for example, cancer recognition. When we have some image of some human organ, and we want to know either it's healthy or this human has some problem, maybe some cancer, maybe some other disease. So we want to classify, and also this task is very good formulated and quite easy to formulate. So quite easy to understand what is input, it is image, single image, and what is answer. It's some single category, like example, cat. Very simple, not very simple input, actually quite complex input, but very simple answer. So actually this is very fundamental task and very well-defined task, and this task can be regarded as some benchmark for different algorithms. So if we know how to solve image classification, then maybe this algorithm can solve potentially more complicated task. But to start from something not such complicated, we can start from image classification. So let's formulate it mathematically. So we need to associate some label Y with some image X. So our input is image. It's represented in matrix of pixels. And our output is category label. For example, dog, bird, cat, cow, but we can assign numbers for each category, and we can answer some number instead of word. It doesn't matter. So it's quite easy function from image to from matrix of numbers to a single number. So it's like function f from x. Map some image into some number. But image can be high dimensional. Actually, we run classification on not such very big images, but even if image not very big, for example, 300 per 400, then if it's color image, we have 360,000 items, because we have 300 per 400 per 3 channels. And it's quite hard to directly design F like, I don't know, like single formula. It's almost impossible to write some formula that describe this function. So what is our basics to fight with this problem? At first, we need to have a data set of labeled images that can be used to train machine learning models. So we will talk about machine learning. So we need to have some images with when we know its labels. So this data set should contain a diverse set of images representing the different classes or categories. So the more images we have, the best result we can do. Then we can use a feature extraction as we discussed it last time. So images are complex. So maybe we should extract some meaningful features, for example, seed features or other type of features that can be used by machine learning model. For example, we can use edge detection, some histograms finding, or maybe more complicated tools like SIFT features, or even, as we see later, deep learning features, but more deep learning later. Then we should represent image by the set of its features. So do some representation, and then we should use classifier or some model, mathematical model. So based on complexity of our problem and size of our data set, we need to choose appropriate machine learning models. There are different machine learning models, like, for example, support vector machines, decision trees. It's classical, more older models, or neural networks, like convolutional neural networks, like more in deep learning, more recent advances. And then we need to train, we need to train our model on our data and evaluate results. So let's try to do it in traditional ways, like it can be even, I don't know, 20 years ago, approximately 20 years ago. It was best that you could do 20 years ago. We can extract some features. For example, we can extract SIFT descriptors and extract features from image to describe its visual contents. So we need to find some key points, and then each feature we can describe using a spatial histogram. I remind you that we used this in laboratory work too. So we obtain some feature vector. Then we can use some classifier. For example, here two examples of classifier support vector meshing classifier and k-nearest neighbor classifier. So we need to divide feature spaces into decision regions. For example, if we display features like points, for example, each feature consists of only two parameters. It's not real, but very simplified. Imagine that only two parameters. And imagine that in this kind of area, there are some features of objects, for example, of persons, and here, for example, of cats. We can draw some line that divide either it's person or not person, for example, person or not person, two classes. For example, we can divide these two classes by some line. Or we can use some regions, and when we obtain new object, we can look on our neighbors. For example, we see some new object, and we look who is similar to this. For example, we see that two cats are similar, so we decide that it is cat category, and if our objects are similar with some images of dogs that we processed before, then we decide that it is dog. Okay, so let's describe. Let's describe general pipeline for image classification. So we start from a data collection step. So we need to collect images and their object labels. How we can do it? We can find some images, I don't know, in web, or maybe store or take from some database, but we need to process images. If we want efficient model, we want that all images will be of similar size and similar for example, brightness. So we can pre-process images by resizing, normalizing these pictures, some maybe some extracting only the main object from this image. So we need to process some images, and then we need to manually, for example, if we know, maybe we have some database with, I don't know, some pretty pictures of cats and pretty pictures of dogs. So we know that this is cats and this is dogs. So we need to assign this label manually. This is first step. Then we should extract relevant or valuable information from image. So features. This is feature extraction. So it can use, as we say, both traditional techniques like based on edge detection and, for example, if more complicated sift, or maybe a deep learning. Then we need some representation. So generate image representation by modeling object inside image. So we need to represent it so take this set of features and make single representation of our object. And then choose some appropriate machine learning model for classification task. And after that, we can train this model. So learn to predict the object label with a given feature vector. So using features, we know how features corresponds to our label, and then when we train on some test data set, we obtain some model, trained model, and we can apply this trained model to some new picture. So, and we can evaluate this trained model performance. We can use some metrics like accuracy of recognition, like precision, and etc. And after this, if our evaluation says that this model trained quite good, then we can use this model to predict classes for unknown images. Okay, so let's use a classical approach. We can use sift feature as feature extraction, histograms as image representation. For example, some classical like SVM or neighbors for classifier prediction, and then obtain some label. Okay, let's go through all steps. At first, we need some data set. And you will need to do this laboratory work, so you will need to use some data set. Which data set do we have? We can start from very simplistic data sets. Maybe the most simplistic data set is the most simplistic data set is actually called MNIST. And what is it? What is this data set? It's like a database of I will choose. So its database consisted from handwritten digits. So we have only 10 classes. So quite obvious classes: 0 class, 1 class, 2, 3, 4, 5, 6, 7, 8, 9. And when we obtain this picture, we need to understand what digit do we so what is this digit? It is 4. What is this digit? It's not such obvious, but it is 7. So it's quite easy database, and we have different statistics with different models that already tested on this model, and it gives different error rates from ranging from 7%, it's quite not very good error rate, to, I don't know, 0.2 for convolutional neural networks, like 0.2. So very good, actually very good precision. But actually we have more complicated databases, like Pascal Vogue challenge. It consisted from 10,000 images over 2 categories. Caltech, more images and more categories. And the very most really big and really famous database data set is called ImageNet. It consists from millions of images, and it says this, but it seems that right now it's even more. It is even more. Let's find ImageNet. What does it say? That today this ImageNet consists from 14 millions of images and more than 20,000 of categories. So really huge database. So it depends how powerful model do you want? Maybe somebody wants a really powerful model, maybe somebody wants quite simplistic model. So here I have some example for you, and in my example I will use, let's see what model I will use. I will use model that is called CIFAR 10. It's very simplistic model. Let's find this CIFAR 10. So as you see, University of Toronto, they collected CIFAR 10 and CIFAR 100. It's quite big collection, 80 million tiny images, but images are very, maybe CIFAR 100 is really bigger. CIFAR 10 is quite small because only 60,000 and very small 32 by 32 color images in only 10 classes. 6,000 image per class. So we have some training images and some test images. So training images to train our system and test images to check. So we will train on these images and we say what is this. So when we have some, for example, this image, we say that this is airplane, or this is also airplane, and this is automobile, and this is bird. And then we will have, for example, let's consider that this last column is test images. So we will not show this. We will show only this. And then we show this image, and it should say either it's airplane, automobile, bird, cat, etc. So I hope that you understand. So as you see here, all images are very small. So we need really a small model, simplistic model. So it will run faster. So, but you in your laboratory work can use any data set you find in internet. So we need some data set. So we can collect by ourselves, or maybe we can use some public image data set. Then we should divide, as I just said, we should divide this data set into two categories: a training set, a set of samples that use for learning. So we learn using on training. And test set examples used only to assess or test performance. If we do analogy with, for example, learning of students, you know that when you study, you take some questions, do some laboratories, but then, for example, on exam, you take some final, I don't know, final questions, and you can answer them. At first you learn at all information, and then on exam you need to demonstrate your knowledge on very fixed number of tests. And for this model it's also similar. So we have more bigger training set, and model can learn on this model set, and test set, and this set is used only to access or test performance. And we can use different metrics. Maybe we will consider only two metrics. It's average accuracy. It's most popular metrics. So it's very simple. The percentage of correctly classified image over total image number. So if we take, I don't know, let's see, if we take, for example, I don't know, 4 images, for example, this 1, 2, 3, 4, and for testing, for example, this 4 image, and we answer airplane, automobile, bird, and this answer deer. So we have 3 correct answer and 1 wrong answer on testing phase. So in this case, our accuracy is 75%. So 3 correct from 4. So we can divide. So we can find percentage of correct answers. And we have one more popular evaluation metric, top N accuracy. So actually, when you run some model, they not answer one category, but they answer different number of categories. So when we take some image, the answer of our model will be the next one. For example, it's automobile with probability 80%. It's, for example, I don't know, airplane with probability 5%. It is dog with probability 4%, etc. So each algorithm actually say not one label, but it give range of bunch of labels, but it rank them from more high probability to less high probability. So if the probability of n estimated labels contain the correct label, for example, top 5 accuracy. So if model says for this database, for example, this is either automobile, airplane, bird, cat, or deer, and it is correct. So it has 5 guesses to guess these images. So if it's correct, we consider this correct. So it's easier to score accuracy with top N. Then, so average accuracy, we can consider it's like top 1 accuracy. So the most probable label should be correct. And here, one of 5 most probable labels should be correct, for example. I hope that it is clear. So is it clear how to evaluate model? So I will ask you, is it clear how to evaluate if we train some model? How to evaluate it? Sorry, can you understand me?
Yes, of course.
So is it clear how to evaluate your model, your performance of model?
Yes.
How to find accuracy? Sorry, I interrupt you. Is it clear?
Yes, of course. I got it.
Okay, let's move then. So our first approach is called SIFT, is used to use SIFT features, as I said, and we know already SIFT feature, but it's proposed by David Lowe in 1999 and then refined. So we should detect and describe some local regions or features in image. They are invariant to size, rotation, and illumination change, and they are robust to addition of noise. and highly distinctive for not only for image matching, but also for classification. So I remind you that some response function should be maximal, both for position and for scale. This makes it scale invariant. Then we rotate our patch according to its dominant gradient orientation, so we can find a dominant gradient and then rotate it. So it makes descriptor rotation invariant. And use normalized histograms to reduce the effects of illumination change. And we make this histogram of frequencies, then normalize and obtain feature vector. So we obtain some numbers after a big image. We obtain numbers if we represent a feature, but we represent single feature. What should we do next? So we understand how to represent single feature, but how we represent the whole image. So we can use a conception that is called bag of words. So bag of words taken from text, for classification of texts. When we have text, then our text with how much each word, each K, how much it percentage of its repetition. So for each word, we need to remember how often it present in our text. And actually, we can use it for images. Object can be represented by composition of local image patches. So that so-called words, so visual words. So this is these features, small areas that typical to compare with other. And let's make a very simple example. Let's choose only 4 features for the visual words: eye, this part of music instrument, cheek, and this how it is it pedal on English? I don't remember correct word. So this is part of bike when you sit, where you sit. If we, for example, take this picture, of course it has eyes, it has that kind of features, but it doesn't have this and this. If we take this picture, okay, then it has this visual word. Picture, then maybe frequency of these features will be higher. So objects belonging to different categories have different frequencies of specific visual words. But we understand that every visual word are different. So how we can divide it, for example, in some categories? For this, we need vector quantization. So we need to use clustering of extracted features, and to cluster, for example, features that look like eye, and then use some central cluster center will represent our visual word, and something that is similar will be classified as this eye feature. So this is this specific eye, and this may be closed neighbors of this. This is okay. So let's continue. So we classify each feature according to proximity to some cluster center. So after this, we need to represent by frequencies, and Lord classified assigning bag of words representation of images to different classes. What is drawback? No, it can be considered drawback or not. For example, important spatial location information is ignored. So these 3 pictures are totally equivalent. Maybe this picture and this picture upside down, they are equivalent. Maybe it's good because really it's the same picture, but this picture will be considered also equivalent. So it doesn't, so if we, for example, some object break into some parts and make these parts across the image, it doesn't matter because it simply counts some features, doesn't matter where. So if it's like shifted, if it's puzzled, it doesn't matter. We can do it to fight with this. We can do it not only at full image, but we can divide images to some subregions and find features and at each subregions. And computing histograms and features for each subregion. Okay, so in this case, it doesn't ignore location of some object. So, for example, if something for example, if head is in something like head is upper, then maybe it's more highly that it's person than if head is downwards. So it not ignore this. In this case, it not ignore the position of some object. So we can use this approach. And then we can train some classifiers. For example, we can train nearest neighbors classifier for one neighbor. So we can take, so for example, this is cars, this is known cats, and this is known dogs. So we have one object that are new, and we don't know who is it. We compute image representation and then look at all other objects and find closest one. Okay, closest one in feature space is cat. Then we decide this is cat. So this unknown object has a neighbor which is labeled as cat. So we decided this sample is predicted as cat. But we can do the same, but with bigger k. So we can predict a label according to its nearest neighbors. Not one nearest neighbor, but several nearest neighbors. For example, we can take 4 neighbors, and this object has 2 neighbors as dog and 1 as cat. For example, it's randomly our dog look like some cat. Maybe it has color with similar to some cat, or it has a form of body similar to some cat. So it's similar. It's randomly appears like some dog is similar to some cat, to some specific cat photo that we have in our database. But it is similar to only one cat, but to several dogs. Maybe it's not such similar to that dogs, but dogs has greater numbers. So we decide it's not cat, it's dog. So in this case, we have different drawbacks. If we take a small neighborhood, we have large variance. So maybe some random similarity can do very much effect. So we have unreliable estimation. If we take too large neighborhood like here, we have large bias and inaccurate estimation. So we need to find optimal neighborhood. And then we can estimate category label for input sample. So if we have input sample X, we need estimate some conditional distribution. So some conditional probability that this object X has label Y. For example, let's take only two categories. For example, 0 and 1 category. For example, yes or no. For example, either it is suitable for viewers or not suitable image. I don't know. Maybe either it's cat or dog. Very simple decision. In this case, and we have some model parameter that we train some model. We can represent it as this. We have some object, we have some parameters that we of our trained models, and we predict some label, some probability of label. And of course, we need to have probability of 1 plus probability of probability should be number from 0 to 1, and sum of these numbers should be equal. So it's because it represents probability. But how we can do it? So what idea? So we have some number. So some number, let's take any number from minus infinity to plus infinity. How we can transform it to number from 0 to 1? We can use this logistic or sigmoid function. Very good. So it's, as you can see, quite old idea. But we have multiple classes. What we can do? So we can apply this exponential function, and we can, using this vector x, we can compute some value for each class, for class Y and each other class K, compute some value using some formula. In this case, we use some matrix multiplying by some matrix, but it can be any formula. And then we need to find exponential of this number and divide it to exponential of all numbers. We can take several numbers. We can find some of their exponents of number this. Let's use different, not very interesting. For example, that one, it can be some minus values. Let's be these numbers. So we need to find exponential of each element and find sum of these exponents. Sum of these exponents. I will use Excel for finding this sum. So we need to find this sum of exponents, and then we need to find exponent of each number. Exponent of this number. Of each number, and then divide this exponent of this number on sum of this exponent. And when we divide, we understand that exponent is always positive number. So, but this exponent always less than this sum of exponents. So when we divide, we will obtain number from we obtain number from 0 to 1. And if we obtain these numbers, then sum of these numbers, of course, because if we summate, then they have a denominator, sum of exponents, the same, denominator the same, and numerator, if we summate over this numerator, then we obtain, of course, 1. So if we summate over this, summate where we can summate, we can use auto summing. And of course, the total sum of these elements is equal to 1. So if our model predicts these values, then we can say that with 83%, if we multiply by, if we represent it as persons, so if we represent this as percent, then each number represents probability. For example, for class B, it's 84%, for class A, 4%, for class C, 1%, and for class D, 11%. And total is, of course, 100%. So I hope that it is clear how this softmax works. So if we take different numbers, then we can use the softmax classifier to obtain what? To obtain probability that some some object X belong to category Y. And then we know correct category label. So on training phase, for each object X, we know correct label Y. So we can find this probability, and we need to maximize it. So we need to maximize this average probability by changing these coefficients omega. So we change coefficients omega for each object X, and we find this probability Y, and we find a maximization of this logarithm because this of logarithm of this probability. Okay, but actually, it can be represented in another manner. It can be represented as cross entropy between true distribution P and estimated distribution Q. What is true distribution? Of course, we know this is estimated distribution. True distribution always look like 1 at or 100% and with one column and 0 in other columns. For example, let's imagine that this object is actually this one. Then we have true representation like this. But our computed representation is this. So if we take accuracy, then we guess right. This is maximal, so we guess this as category B. But to use cross entropy loss, so not only that we guess, but how confident we guess it, we need to find this cross entropy. And we should minimize this cross entropy. So our distribution should look like this. It's quite close. It's good. But how to find how it differs? We need to find using this formula. And using this formula, we will obtain minus. Here we obtain 1 for one class and 0 for any class. And then logarithm. So it's the same like here. So it's how to say, it's a reason for this formula. So we need to minimize difference between this true distribution and this estimated distribution by using this formula. And here it will be 1. Here it will be a logarithm of this one, estimated, that we find using this formula, softmax classified. So we need to find minus logarithm of this. So this is quite good. But if we, for example, this is, and it will be called a loss function. It will be called cross entropy loss function. And we should minimize it. So it's already good. But if we imagine that it's not that case, but in reality, it's this category. And not second, but this category. In this case, we need to find minus logarithm, minus logarithm from this one. And in this case, loss function will be much worse. So bigger loss function, worse. And we should minimize this loss function, minus logarithm. Okay? How we can do it? For example, we can use support vector meshing. And what is this classifier? Imagine that each feature is represented by 2 numbers. So x and y. So on hyperplane or on simple plane. Our space is 2-dimensional. So each point has 2 coordinates, and we can divide this space into two regions using line. So some line divides this region. So this is hyperplane, is line. So some line divides it into 2 parts. In 3-dimensional, some plane divides this space in 2 parts. In more dimensional, more complicated this division surface will be. So we need to find out this linear decision surface, so hyperplane. How to find them? So, for example, if we have some negative instances and positive instances, we of course can use any of this line, and it seems like normal. But what line should we choose? We should maximize the gap for linearly separated data. So we should choose this line. So our gap, so distance, if we move this line to the left or to the right, so this gap should be maximal. So we use this line, not this, for example, line. or not this line, but this line. So separate samples to have the largest margin between two borderline samples. This is called support vectors. So it can be represented in vector form. And to maximize this gap, we need to minimize this one. I will not talk in details how to do it. It's some other subject. It's called machine learning and or I don't know clustering or some data science or some. So it's I also only say that you can use support vector machines, or you can use K and K nearest neighbors, as I said here earlier. But let's move to deep learning. So this was some traditional learning, and it was quite effective. But if we compare, for example, let's look our Wikipedia for this quite very easy base, MNIST. Traditional methods, what they have, for example, SVM has quite good, 0.5, quite good. K nearest neighbors have similar, 0.5. So this is two best traditional methods, SVM and K nearest neighbors. But we can use neural networks. If we use shallow neural networks, two-layer networks, then we have even worse results. But if we use deep neural networks, and especially convolutional neural networks, results will be much better. So you can see that results of deep learning algorithms are better on this simple model. For bigger model, the bigger number of pictures do we have, better deep learning work. So deep learning work good for big data. So let's talk about deep learning. What changes? What problems with traditional learning? In traditional learning, we do manual feature extraction, we do manual image representation, we select by ourselves classifier or some method, and then only training on classifier. So we train only classifier, but we choose features, we choose representation, we choose classifier type. Through building and training neural networks, deep learning proposes to jointly learn feature extraction, image representation, and classifier. So we take the whole construction in the single deep learning network. So this deep learning, on first steps, they use feature extraction, then it use image representation, and then on last stages, it do classifier. But features is automatically learned, so we don't need to talk about what features do we use. Representation given also automatically, so we just need to create architecture of this neural network and then train. Of course, it needs very long time to train this and very powerful hardware. We need really very powerful hardware. For example, when I want to learn this deep network, or not deep net, deep learning network, so CNN, so convolutional neural network, on my notebook with a quite old notebook with built-in video adapter. No. It's too long. So I will use. I had to use Google Colab to learn it in cloud system. So, but we have superior performance on large-scale databases. But a disadvantage that we have unclear decision-making, black box. So it works, but how it works, we don't know. So this is deep learning. Deep learning approaches, its big disadvantage that it works, it definitely works. We can evaluate that it works good, but we don't know how it works. So we know how works SIFT features, but we don't know how works these features in deep learning. We can try to visualize them, to evaluate them, but it's very hard. Okay, so it's quite similar to our brain, the human brain. If we study our brain, then also we have different areas where we as humans detect edges, we detect some primitive shapes and then higher shapes. So at first some edges, then some parts, and then we can learn some, for example, faces. So we recognize some faces. So in deep learning, we learning some hierarchical representation. At first, we learn low-level features like simply edges, some gradients, some changes in how to say, changes in light, in intensity of picture. Then on mid-level, we have more complicated features, and then even more complicated, and etc. So how this model look like? So on input, we have image. And then we don't use feature extraction by itself, but we apply this image to some deep network, and we extract features. So our deep network will do feature representation, and at the very last, how to say, very last layer. So we have different layers. On first layers, we have feature extractions. On the last layer, we have softmax classifier. After the softmax classifier, we have a vector of label probabilities. So for this picture, for example, our probability will be, for example, probability that cat is 0.9 or 90%. So 90% probability that it is cat, dog only 5%, cow only 3%, and car only 2%. So we decide that this is definitely cat. So what is pipeline? First, data set collection, then network design, and then network fine tuning. Data set collection, so we need large amount of training samples, really large amount. So you can see that accuracy, we take, for example, face recognition, and we use different data sets and different systems. At first from small data sets and bad recognition. Bad recognition, how to say, accuracy. So only 85%. But then we use very big data sets 4 years later with more than 100,000 images and accuracy of recognition much better. But of course we can make training data and test data. Of course we discuss it. But we can use, for example, training data and test data and try out best hyperparameters on test set. So train some neural network and then find best hyperparameters and then try to run it on test data. It works, but it works quite bad. Why? Because in this case, you can find overfitting. We need to consider this overfitting more in details. So what is actually overfitting? Neural network. So very good image in this case. I can find on this, explain your overfitting on this single image. On these points, we need to approximate how they form. So these points, it's like we need to understand how some parameters change over the time, for example. So how parameter x is linked with parameter y. We can approximate our function, our function, our allow how parameters one dependency between these parameters as line, but it's not very good approximation. Maybe it's better approximation this one. This one is good. So we see that parameter y at first decreases and then start increasing. And here is we have minimal parameter y. If y is some cost, for example, and we should minimize, we should take this x, for example. And this is good approximation. But if we really try hard to approximate this function, that we can find this function. So it's very detailed. It's not very detailed. It's very simple. It's just right. It's too detailed because it's too prone to some random changes. So it's change very rapidly. So it's hard to predict, hard to how to say, to it's very complicated function, but really reality is more simple, but we have some noise, some randomness. It's not such complicated. It's not such complicated law, but it's only a random variation. So this is this overfitting when model tries to learn too many details in the training data. So they learn about noise in training data. To fight with this overfitting, we need some validation data. So we need some training, and then checking inside of training, checking our train results on some validation data. So when we check it, we can we can understand either our hyperparameters are good or not. So let's talk about network design. So because of this, we need to divide our data set not only on training and test, but training, validation, and test. So we train on this. We validate after training on this, and we do it several times. And then final examination, we test on this. I hope that you understand this concept. Then network design. We should use some neural layers, and we can combine different types. In principle, we can use different types of neural layers, but maybe the most important is convolutional layer. Also, we will use pooling layer, fully connected layer, and batch normalization layer. So we need to construct different many layers. So what is deep neural networks? So not deep when we have shallow networks. If we look at this monist, for example, this is not deep learning. This is regular networks with only two layers. It's not deep learning, and it works bad, as you can see, even worse than best traditional approaches. Then, for example, nearest neighbors or SVM, support vector meshing. But deep neural networks work better. For example, 6 layer or 13 layer or 35 layer. Okay. So deeper is better, but we need to control number of parameters. So plenty of parameters, bigger model, and too many parameters, too complicated model, and maybe poor performance. So we need some balance. And this balance is not very easy to achieve. So let's consider some examples through the time. The first known deep network, LeNet, with 5 layers. Then AlexNet, 6 years. No, not 6, 16 years. So very big time gap between these. 7 layers. Then it fastly deep learning became very popular. Many scientists start deep learning researches, and as you can see that for example Zisserman, Simonyan then create VGGNet with 19 layers, GoogleNet with 24 layers, and ResNet even more than 1,000 layers. And this is not the end, as you understand. Let's see how it look like. At one stage, we have a convolutional layer and pooling layer. So this pair, I will describe why we need this combination a little on next slides. And we use several stages. So this is one stage, convolution plus pooling. So here, convolution, pooling, convolution, pooling, convolution, pooling. So this is like low-level features, mid-level features, and high-level features. Then this is 3-stage, but we can use more than 3-stage, of course. And after this, we have a fully connected layer, and we should have softmax activation on the last fully connected layer. And at the end, we need to have our class labels. So let's see. Lenet. It works on this MNIST that we see, this database. So at this MNIST database, we have input 32 by 32 pixels and 3. Oh, no, sorry, not 3 channel, because it's black and white. So it's only 1 channel. No, it's not color image. It's black and white image or grayscale. I'm not sure even more. It's pure black and white or grayscale. Even maybe even pure black and white. Simply black and white, not grayscale, but only black or white. So very simple image. So like 32 by 32 bits. And at output, we should have 10 categories. Why? 10 neurons. Why 10? Because we have 10 categories. So number of neurons should be equal to number of categories. Because at the output, we will have probability of each category. Then we have 2 stages. We have some convolutions. And do you remember what convolution actually can do? Convolution can, for example, do you remember, you do laboratory work 1. It can use softening, blurring, like Gaussian blurring, for example, using convolution. It can compute sharpening, but it can find edges. Do you remember find edges? Or, for example, Sobel or Laplacian operator. So this convolution can be very useful for different tasks. And they can find features of some quite simple features. And we will use this size because actually in Linear 5 convolutions are taken 5 by 5. And when we take 5 by 5, how we should draw this? I will draw it in Paint. When we have this matrix, (32 by 32), and we can place this filter from this to this. So center of filter will be, because 5 of 5, you need several lines here and several lines here. So center of filter will be moved through this smaller rectangle of only 28 by 28. Because of this, we obtain after applying this filter, we obtain not matrix 32 by 32, by matrix 28 by 28. We talk about it when we talk about convolutions. So let's return to our features. So we obtain six different convolutions. Which one? At first random, but then we need to train to find optimal ones. So each one has its kernel. And we obtain these kind of features. But what we should do then? We should downsample, subsample. Do you remember that at first we look on small details, but then we should, using some summarization, so we obtain this matrix 28 by 28, and it's too big. So we have, for example, what is twice downsampling. Is it twice? Yes, twice. So we obtain some numbers. For example, result of features 7, 9, 10, 12. And do you remember that we only interested in maximal? So when we find, for example, corner, big number means corner, for example, or big numbers means edge. So we actually interested in maximal number. So we take only one number from this four. It's called max pooling, and then take one or four numbers 1, 2, 8, 7, and take only maximum 8, and etc. I hope that it is clear. So this is called max pooling. So after this, we obtain 6 features, but more with less size, with twice less resolution. Then again convolution, but not 6 features, but 16 features. Of course, when we use convolution, we crop edges, so they are a little bit smaller, so 10 by 10. Then we obtain 16 features, we downsample them with max pooling with 5 by 5, 16 5 by 5. And if we take this 16 5 by 5, so this tensor, so three-dimensional matrix, 16 by 5 by 5, it's how many numbers? It's 120 numbers. We just flatten, restructure it. So we just take each number one by one, and we have this layer with just 120 numbers. After it, we have fully connection layer to 64, or I'm not sure, 80, 84 or 64 on less numbers. And then at last we use softmax, I'm not sure, but yes, softmax. Convolutional pooling, convolutional pooling, fully connected, softmax. We use softmax at the last step and obtain 10 categories. So 10 numbers between 0 and 10 probabilities. 10 probabilities of each category from 0 to 1. And their sum is equal to 1. So this is simplest architecture by LeCun, by this LeCun, Poitou, Benjo, Hafner. It's quite old architecture, very simple architecture, but it works. Next example, more layers. AlexNet on ImageNet, it was winner of 2012, so it's like 10 years ago, more than 10 years ago, and very remarkable improvement in image classification. Best traditional method on this ImageNet, very huge database, works only 73, and ImageNet 84 accuracy, 84% accuracy. Okay, let's see. At first, we have what? Convolution. Then max pooling. Then convolution. Then max pooling. Then convolution. Then max pooling. So convolution, max pooling, etc. And then we flatten and use dense layers. You can ask me why we don't use dense layers in all. Why we need some convolution? Why we cannot flatten at the beginning and simply use dense layers? Of course we can. But if we flatten, so if we just, what is actually flatten? When we have this matrix, we just convert it into very long vector. Using flattening, we lose this space. So all pixels look like the same. And we lose concept of neighbors, pixels that are neighbors. So we lose this connection between pixels. We just take a lot of pixels, and if we lose it, it's very hard to train this very large, and we have a lot of pixels. Even 32 by 32, it's a lot. It's 10,000. Oh, sorry, 1,000, approximately 1,000 pixels. It's too big for fully connection layers. So we need not lose this structure. So we need to use some concept of neighbors, and this concept of neighbors, it's moving shift window with some kernel. It's convolution, like we use in laboratory work 1. So you can see that using these tools, we can quite simple structure, we can achieve quite good result. VGGNet, much better result. Not 84, but 93% in the same ImageNet data set 2 years later, 10 years ago. It's much deeper than AlexNet, but actually it used convolution, convolution with pooling, 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 fully connected. As you can see, nothing changed globally. So it's much deeper, much powerful, more complicated, more hardware, needs more powerful hardware. These deep networks need to be training on GPU, not CPU, not on central processor, but on your graphical GPU, graphical card. But as you can see, it works similarly. So how we can fine-tune this? If we know design, how we fine-tune? So to fine-tune, we need to define loss function. So we need to define the objective function that measures difference between predicted result and grounded truth. So this is difference between what we want and what we have. So between predicted and real result. This is loss. The less we are happy if it's small. And some optimization strategy. So how change network parameters, how they should be updated or fine-tuned to minimize the loss. So which loss function can we use? We can use sigmoid cross entropy loss, or we can use softmax loss, as we say about we say about softmax already. But let's consider in details. We have some training samples. So N is the number of all training samples. V denotes some parameters. So S is output class probability of the network. So we have S y eta, y, it's score of correct class. This is good. And S j is Sj is score of J class, so any class. And do you remind our formula? What we need to have? I will show Excel. We need to find sum of all exponents. Here, sum of all exponents. We need to find exponents. Oh, no, these exponents. Okay. We need to find exponent that are real. For example, it's bad example. It's like bad prediction, really bad prediction. We predict this, but real is this. So 4%. If we find this one, this will be 0.04. Only 4%. That this is, for example, class 1, but it is actually object of class 1. Then we should find minus logarithm of this, minus logarithm that I illustrate on this picture. And this will be Li. And then we need to find some average loss. And we can use some function of parameter regularization. Why we need parameter regularization? We need more simple parameters. If parameters are big, are very complicated, we don't need this. We need small parameters, smaller. But of course, if we take all parameters as 0, it's best parameters, then our network predicts nothing. But we need some small parameters, but they give good results. Smaller parameters, but best results. So we penalize big parameters. And we can use different fine-tuning. Stochastic gradient descent, the most simplest method. Momentum, Nesterov accelerated gradient, Adagrad, and etc. So, for example, adaptive moment estimation. So what is actually and here we can see on this slide how it look like. What actually we start from this mistake. To minimize our, so we start from high points, from high mistake, and we want to minimize it. So we go through this. Some, unfortunately, some methods stops here or long being here. This is a local minimum. So we go in left or right and find this point, but it's not optimal. But some points of some algorithms goes to here, so minimizing or with real minimizing. So as you can see, some algorithm works faster. Some so different convergence. Some very quickly goes to best, and some very long time. So okay, so I'm not sure we should move fast, then, but okay, let's see. It's not my task. It's I don't remember whose these slides is originally, but author of these slides provide some data set, food, 101 food categories with that number of images, 1000 per category. All images side lengths of 512 pixels. So square images, 512 per 512. And you can use some details, but this is Berkeley. This is slides of Berkeley University. You can use any. So here is advice which you can use architecture from this. You can use different functions and find this convergence and find how each model works, and some sources, books, video courses, and etc. But I will display you my example. So I will give you these slides. I will send you these slides. So I need a chat. I need to use chat. Where are these slides situated? So I have for image processing, and actually I need a lecture 8 image classification, this one. No, nothing happened, like here. And I can write, this is slide lecture, slide of the. This is slide of who is its author. Unfortunately, I haven't write it. Who is author of these slides? Okay, doesn't matter. But let's consider my example. So I take CIFAR datasets. What is actually this CIFAR datasets? This is it can be loaded, uses this load data. I use TensorFlow for machine learning. I hope that you know what is TensorFlow. And I download train images, train labels, and test images, test labels. This is for training, this is for test. Then I use class names. For example, class names, this is fixed class names: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. Then I want to simply, I don't know, simply show, for example, these images. I can use using a CV to open CV, but actually I cannot use if you use notebook, Python notebook, you can use CV2 I'm show, but in Google Colab it doesn't work. So I use some patch. It's called this function CV2 I'm show that simply shows this image in Google Colab. So we print class name for some label. And then we only look at first 10 pictures. We take, we show this picture, but before we show picture, we take class name of most of real train label. So this is frog, this is truck, this is also truck, this is deer, this is automobile, this is automobile, this is bird, this is horse, this is sheep, this is cat. Actually, it's quite hard to see. It's for such small images, it's even hard for human to understand. Is it bird? So maybe is it horse? Yes, of course. Is it sheep? Maybe. Is it cat? Oh, very hard to understand it. It is cat. It's lying on ground. Okay, so I simply show something from this data set. Okay, then I need to normalize, because my pictures they have colors with from components from 0 to 255. But neural network works better with a number from 0 to 1. So I will normalize them. Then all values should be between 0 and 1. Simply divide it by both train images, both test images, but divided by 20, but by this maximal number. Then I create a CNN, define CNN architecture. So I take one convolutional layer, then max pooling, then convolutional layer, then max pooling, then convolutional layer. I'm starting from 32 features, and input shape for me is 32 by 32 by 3. Then I use max pooling. I in twice how to say, I decrease dimension twice. Then I use 46 features, and also 3 by 3 convolution. Then also max pooling. Then also 64 convolution. Then I flatten it. Then I use dense layer with regular activation, like ReLU activation. And on last stage, I use a dense layer with softmax activation function. And of course, it is 10 categories. Then I compile this model. I use ADAM optimizer. Do you remember when we speak about optimizations, how it can be? Where is it? Not here, not here. Here. So we can use different optimization network, different strategies: stochastic gradient descent, Nesterov gradient, and yes, adaptive movement estimation, ADAM. It's one of these methods. Then I use cross entropy functions and use matrix accuracy for evaluation. Then I train my model using train image and train labels and 10 epochs. And for validation, I use test data. Maybe it's not the best solution, I think right now. So I use test data for validation. But okay. we will see what happens. And then I evaluate my model on test data and print accuracy. Should I rerun it? Maybe I should. Let's try to run it, because you should see how it works. So I start execution. It's run it all. It's in Russian, but I need command run. So, like, I need to run this. So at first it's downloading. It downloads this data. So it's downloading this number of bytes. So this Google very fast downloading. So it downloads this 170 approximately megabytes. Then it prints these pictures. Then it create this and start. So it create this model. It compile this model and start. As you can see, it's now training. How it look like? So you can see that it's okay. So I changed it a little bit, and maybe I changed it not the very best, but it works. So how it works? You can see that loss is constantly decreasing and accuracy constantly increasing. So during this first epoch, we study our model on each sample. Our loss decreased, our accuracy increased, and after the end of this study, we obtain some values for a loss function and accuracy during on this. So we train on our train data, train images and train labels, and constantly checking our loss function. So we minimizing it. It's constantly less and less, and hopefully accuracy will be rising, but we minimize loss. And when we minimize loss, accuracy goes higher. But on validation data, and we use our test set as validation data. As I said, maybe it's not optimal solution, but anyway. So on validation data, we have increasing of accuracy. As you can see. So this is our database. It's 10 classes. These pictures. Very simple, very simple, very simple database. And here in Colab, you can see that each epoch we train our network. We constantly decrease our loss, but not constantly. Actually, you can see in some cases we have increase of loss, but in general we have decrease our loss, and our accuracy goes up. So we start after end of first epoch, we start from only 45 accuracy percent. That's low, quite low accuracy, but right now we have 86%, even more. And we have a different accuracy on validation, our validation set. So I remind that we have used our train data as validation. Oh, no, not train, test data, test data set as validation data. So we need to wait for epoch number 10, and actually so I use softmax. So it says that sparse category entropy is not the best for softmax. Okay, let's so I need to change it a little bit. So I need to use categorical cross entropy. So So I need to use optimizer, let it be Adam optimizer, but a loss function. I need categorical cross entropy function and matrix accuracy. But I use what? I use sparse categorical cross entropy. So I use not correct function. So maybe it's better to use here categorical cross entropy. Like I written in slides. But let's wait for epoch number 10 because I need to show you results. So I will not rerun with categorical cross entropy. So I slightly misuse this model because maybe sparse categorical cross entropy for other type of activation. But if activation is softmax, it says that something not very good. So for softmax and not represent logits. So maybe I need this one. But we will see how it works on this non-optimal results. What I can say, I can see that loss function constantly decrease and accuracy constantly increase. It is good, but not all is such good, because if we see situational validation data, so I use my test set for validation, we see that at first everything goes very well, and our accuracy goes to 70% on validation set. But then, unfortunately, as you can see, it stabilizes. So it's like overfitting, maybe not very big overfitting, but you can see that accuracy increased on training data, but on test data, it is not increasing. So if we look at graph, we look at graph after it's done very, very soon. So as you can see, our training is over, and then we test on our test data. But of course, our test data is equal to our validation data. Maybe it's not very good, but we see the same number. So test accuracy. And if we plot our accuracy, then our accuracy on training, of course, it increases. Very good, very steady, but not very rapid, but quite steady. But this accuracy of on set of for validation, it increases, but quite slow, quite slow. Okay, so let's. It is over. It seems over. Okay, and let's see. Our model is training. Its accuracy is quite good. It's maybe approximately the same as last one. Nothing changed. This is quite a simple and non very effective CNN architecture. And I can say about these numbers. These numbers, you can ask me why I use these numbers. Of course, I use 10 because we have 10 classes as a result. It's of course. I use 32 or 64. I'm not sure why. It's my choice. And I use 2 max pooling and 3 convolutional. Why I not use even 1 more max pooling? You can experiment. And how this layer do you have? What numbers do you have here? It's called hyperparameters, and you can experiment on validation test to change these hyperparameters. So this is very easy solution with no fine-tuning of these hyperparameters. So in this case, I use these hyperparameters by my choice. It's not very good because you can actually fine-tune model to choose best the best parameters, the best hyperparameters by yourself. But this, as you can see, this model works and achieves 70% of on test set. 70% it's not good, but it's better than nothing. Maybe somebody of you will be able to create a better model. Okay, well, 71%, wow. So in this case, it goes up yet, 71%. Maybe if we take more epochs, then I will obtain even bigger. I'm not sure. So you can, you should check your results on test set. Results on the training set, it's good, but it's better to have best results on test set. Okay, so I'm not sure, dear students, I'm not sure if it's too, I apologize for long lecture, but it's quite complicated topic. Is it too late for you, or should we move our laboratory work on next Friday, or should I check your works today? What should I do? So our lecture is over. Do you have questions on our lecture?
No question. It's so clear. I understand.
So your task is to do this in image classification. So it's up to you to choose some model, to choose some set